What if we provide 125? Means I'm not following the code. So some designer will say you're not following the code. Your design is unsafe. Your building is going to fall down because you didn't follow the code. That's what the designers say and think. Is it really going to happen? 100 to 125? Is it going to change the building from not falling to falling? Obviously not. But can you say that? How can we prove that it's not correct? So we will see what is the significance of these numbers. Does it mean failure? Will confinement be really lost? And will 100 be enough to confine concrete in a particular beam, right? What ductility does it provide? 100 millimeter spacing, what ductility does it provide? What ductility does 125 millimeter spacing provide? What ductility do we really need? Do we really need the ductility in this beam? Because maybe this beam is not the primary beam. There's a shear wall close to that, or another place which is taking, or another big beam which is taking the load, not this beam. So many questions arise, and if we simply blindly follow 100 millimeter spacing for every beam in the structure, well, we are following it, but we don't know what is the outcome. Performance-based design has totally different approach to this problem. In that approach, we say, use the actual beam section, first of all, not any beam section, and provide longitudinal bars and the spacing, diameter and size. Compute the confinement that will be provided by the spacing, whatever spacing that is, 100 or 125. Generate the confined concrete model. Determine the moment curvature for this section and moment rotation model, and define a hinge with those properties. Attach appropriate hysteretic model for the cyclic damage. Carry out nonlinear analysis where demand and capacity are linked. Determine the rotation at that beam and check if the rotation now is okay or not. So 100 millimeter, 125 millimeter, 100 millimeter, 200 millimeter, they might give a little bit slightly different. You will find later, I will show you a slide, hardly much difference in the confinement or the moment curvature or moment rotation capacity provided by 100, 125, 150 and 200. But the codes would have us believe that if you go 1 millimeter above 100, oh, something's going to happen. So performance-based design gives us the opportunity to look at the things more realistically. Then we can check each beam, and wherever some beams may need it, some may not need it, some may need less than 100, we do it, right? But we cannot just follow blindly the codes everywhere. So that is the key difference between the code provisions and the performance-based design. The code provisions just tell you to do something blindly. Performance-based design says that check it explicitly with all the possible knowledge that you have. So these are the modifications. I think I've already mentioned all the modifications. So this basically is not arbitrary. This is specific to the structure, to the side, to the beam, to the column, one by one. We are not treating all the columns the same. We are not treating all the beams the same. We are treating each individual column, beam, wall, footing individually, specifically, based on its own merit. For tall buildings, this has become now a more important topic, because for tall buildings, the documents that govern tall buildings are no longer the design codes. They are not sufficient. They are not applicable. So these are the documents. You can see here, you don't see ACI code here, you don't see Euro code here, you don't see BS code here. The traditional codes are all missing because they don't govern the tall buildings anymore. These guidelines do. The engineering community does. So we follow this one. This one, most important now is pier, especially I'm talking about earthquake, and also for wind. The traditional codes do not necessarily govern the design of the tall buildings. So these documents are more international, and they are more of a help to the engineers rather than restriction. So we know why we should do performance-based design. Now the thing is, what are the basic components of a performance-based design. First of all, multiple performance levels are checked. So we can check the performance at multiple levels, not just one level, explicitly. Number two, multiple seismic events are applied. So hazard levels could be different also. We check them explicitly. May utilize nonlinear analysis. Actually, I should say must utilize nonlinear analysis, which a big kind may utilize. Detailed local acceptance criteria for structural elements, for non-structural elements, we can check in detail. Each beam, each column, each wall can be checked locally, and acceptance criteria can be verified. So we can say this earthquake will damage column number that and that, but not this. And this wall will be damaged, but not that. So we should be able to come to that kind of understanding about the structure. So let me go a little bit. Okay, hazard. First of all, earthquake, hazard. Basically, it's all probability, as you know very well, right? So we are talking about probability. And probability we can define in a number of ways. So the event, we can say that, okay, we are talking about the probability that a certain level of earthquake will occur on certain fault, or we can say a certain level of earthquake will come to this site with this intensity in a certain number of years. Doesn't matter where it comes from. So two different things. One is that a fault will rupture or crack, let's say in 1,000 years, and has the capacity to generate a magnitude 7 earthquake. Okay, that's good. But my building is somewhere else, and my building may be affected by many faults. So that means we need to do this in detail. We not only have to see what are the faults and what are their capacities, but also how many faults are there, how often they generate, how far they are. This will be this topic. I'm not going to go into detail at all because we have a special topic on this one, on site-specific determination. So that will be discussed later. Okay, so I'm just going to skip that. But basically, we will get some idea of what the earthquake risk or hazard level at that site will be. And that can be defined in these categories. We can estimate the hazard level in these categories. We assume that the life of the structure is about 50 years, let's say. In that 50 years, we can say an earthquake 50-50, 20-50, 10-50, 2-50. That means 50-50 chance of that occurring. 20% chance of that occurring in 50 years. 10% chance of that occurring in 50 years, and 2% of chance. So these tell us frequent, occasional, rare, very rare earthquakes. Now we can say that, okay, I want to design my building for these earthquakes with different performance levels, depending upon what type of structure I'm designing, what is going to be the life of the structure. If the structure is temporary structure, it's only going to live for 10 years, my definition of the earthquake will be changed, because 50 years will not come in. 10 years will come in here. So the earthquake level will change because the life of the structure is shorter. On the other hand, we have a project in Bangkok these days. They say it should be designed for 100 years, life, not 50 years. Normally, so now the design life of the structure is 100 years, which means now we have to take care of a higher level of seismic hazard because 100 will come here. So this one will be higher. So we have to design. So buildings which are designed to last longer must be designed for a higher hazard level. Buildings which are designed to live shorter can be designed for a lower hazard level because of the probability coming into that picture. So with this one, we can define what the earthquake level will be, and at the same time we can say what do we expect the structure to do for that earthquake level. For example, for frequent earthquakes which will come often doesn't mean every day. Often means maybe once or twice in the lifetime of the structure is already often, right? Definition of often is also strange, you know. Often means once or twice in lifetime is often. Those structures for those earthquakes, we need our structure to be serviceable that means no damage, nothing. It should shake the building. People should be, if I'm doing the seminar, if an earthquake comes, we should continue to do the seminar, maybe stop a while and continue. But we shouldn't have to run out, we shouldn't have to be scared, no damage, no nothing. Second level is design basis earthquake, which is coming rarely, once in a lifetime maybe. Once in a lifetime and also maybe. Code level, this is the code level earthquake. And that one we expect certain damage. But not too much. We expect the structure to become nonlinear. You know, all of you who design, you have seen a factor in the code called R factor or response modification factor. We will talk more about that a lot. Basically, it assumes that the force which is coming to the structure is not the one that we can design for. So we design for a value much less than that, 1/4, 1/6, sometimes 1/10 of that. And that reduction we are expecting to happen because of the damage and energy dissipation and other factors. So which means that we are expecting that this earthquake that will come once in a lifetime, maybe the structure will be damaged, but not too much. What is too much? Okay, that needs to be defined. Then we have this maximum considered earthquake, MCE. That is the maximum possible earthquake that can come to that site based on the faults and based on the scenario, based on everything, based on what we know about the earth. Of course, we don't know everything. Something other can come later. But that earthquake, we say there's a 2% chance that that might come. And for that, the performance is collapse prevention. Just do not let it fall down. It may be damaged heavily, but should not fall down. But if you tell this exactly to the public, they will still be not accepting even this risk level. They will say, no, I cannot accept this. But the cost of not accepting is too high. We have to accept it, practically. Otherwise, we probably can't design a structure realistically. Right? But somebody can say, some client can say, like for example, the nuclear power plant in Japan, which is having trouble, is one of the examples, where you can say, no, even this earthquake, I don't want to expect any damage. It must be serviceable, even for that earthquake. Sure, we can do that. So we simply change the performance criteria for that structure, maximum considered earthquake, serviceable. And we design for that. And we can. And we should, probably, because the consequence is too great to accept. So the consequence of not conforming can be built into the selection of the performance indicators and the level of earthquake. So that is how we can adjust what we want. The client, the public, and other people can agree what performance do we need for different levels of earthquake, and that's what makes performance-based design interesting, because it lets other people come in and make the decision. So performance levels. This is permissible amount of damage given the design hazards are experienced. That is the definition of the performance level. What is permitted to happen in a structure if a certain level of earthquake comes in? If the level of earthquake is more, then that's a different issue. There should be another performance indicator. But for a given earthquake level, let's say we say earthquake intensity 6 at 50 kilometers from here. If that happens, what should be the expected performance of this structure? What should be damaged and what should not be damaged? So in that way, we can define the performance criteria and then we can design correspondingly. So engineer can say, yes, I can look at the yielding, buckling, cracking, deformation and so on, because that's what he knows, that's his language. The owner can say, will the building be safe? Can I use the building after the earthquake? How much will it cost? And so on. So now this damage that the engineer has information and this can be related together. Because yielding, buckling of members can be limited. We can say, okay, we will not let any column be damaged, but we will let the beams be damaged. We will not let shear wall be damaged in shear, but we will let it damage in bending. So we can clearly say, this is what we will allow this to happen, and we check and we ensure that. Then it should be agreed upon, and then we can look at it. So this is, for example, a typical scenario of a performance-based levels, KPIs levels. So we can say operational damage or loss 0%. Immediate occupancy, an earthquake comes, maybe you are a little bit shaken, you go out of the building, come back and start work again in 15 minutes, right? After talking about the earthquake a little bit, and then immediate occupancy, we continue from there. Then life safety. That means building is badly damaged, you probably cannot come in. The lights are all out now, the signboard is falling down, right? You can't use the building anymore after the earthquake, but you were safe. Nobody got hurt, right? Collapse prevention. The building is almost falling down, but not fallen down, but almost falling down. It can be repaired. It has to be demolished after the earthquake, but not much loss of life occurred. So the damage is about 99%, not 100%, almost gone, but not gone. So some percentage we always give. So this is how we can define the performance levels, and then we can define what does it mean, this one, what does it mean, how much rotation, how much crack width, how much damage we can expect. Now please remember one thing, we will talk about the capacity-based design tomorrow. The bending moments and shear forces do not cause collapse, it's the deformation that do. The deformation due to the actions are the cause, not the bending moments. So that means our concern is not the forces, but deformations. So all the limits in performance-based design are set on deformations. We don't care about what the force is. We only care what the deformation will be and try to limit those, because collapse happens because something bends too much, not because the bending moment is too high. Something can bend in a small bending moment also. Another member may not bend at all even for large bending moment. So the bending moment itself has no measure into the collapse. It is the deformation because of the actions. So we limit ourselves to the deformations. So operational level is defined like this. I don't want to waste because we have to move along. But you can read this one in the slides. What does it mean, operational level? What does it mean, immediate occupancy levels? So negligible damage, building is safe to occupy, limited interruption, losses less than 15%, and so on. So you see, clients will like that because losses less than 15%, so they can understand this concept. Life safety and collapse prevention. So you can read about these details. So how do you judge the performance acceptability? Acceptability now is, so we have said that, okay, I want a life safety criteria. How do I get it exactly, actually? What does it mean? What are the limits that I should check now, right? Those are drift ratios, most important. How much the building will tilt. That will tell you almost everything about the building that you want to know. One of the most important key indicator that we check in a building is the drift ratio. How much one story will deform with respect to another story. Because that has everything built into that. Damage, structural damage, non-structural damage, P delta effects, everything is related to that particular number. So we try to measure drift ratios very, very seriously. Structural component deformations, other deformations will also be measured, but they are mostly related to drift ratio, but they can be measured independently. Global, roof drift, and base shear. So these are the things that we may try to measure. So basically, we have very few things to measure, few deformations to measure. And if we can limit those deformations, damage will be controlled. And we don't care, really do not care about other things. As long as brittle failures are prevented. We will talk more about that. And which is again back to the relation to the deformations. So we can say the performance-based design, we can draw the curve between force and deformation. I will talk a lot about this on the second part of the lecture today, which is on nonlinearity. But we can draw this curve, idealized curve, and on that curve we can mark each of the performance acceptance criteria. This is the elastic range. This is the immediate occupancy. So even at immediate occupancy, we are expecting the elastic range may have just been reached. Small cracking may have occurred, not perfectly elastic. It may have just yielded a little bit. Collapse prevention, and this one here. So collapse prevention is here, and life safety is here, because this is where it's going to fall down. So we try to keep our structure just before it's falling down. That is collapse prevention. And life safety is here. Extensive damage, but far from collapse. So there's still sufficient factor before it falls down. And then we have the fall down. Right? So this kind of curve, we can normally say this is 75% of this one. So these limits have been derived based on tests on real structures, observation of real structures, test in the lab, and so on. So these are, again, 75% is a round good number. You know, people, engineers like to do that. Not 72%, 75%. So that tells you that this is not really a real number. It's just a estimation, good estimation. So we should take these numbers as good estimations, not the word from above. This is the secondary. No, that was, please let me go back. This is interesting. This is the criteria for primary members, columns and beams, primary structural members. Then there are secondary structural members, secondary members. Their performance criteria are different. Collapse prevention, they are allowed to actually be damaged in the current code provision, current guidelines. So we are expecting the walls to be blown out. We are expecting the non-structural elements to be completely gone. But now, people are saying, no, this provision is not good. We don't want this to happen because the non-structural damage is causing more harm than structural damage at this time. Because equipment that is damaged is too expensive, more expensive than the building. Like, for example, you have a supercomputer lying in a building, and you're trying to save the building, which has no cost compared to the computer. So the non-structural damage becomes significant. Equipment must be saved. Normally, the walls fall on people and hurt them. So non-structural damage of the wall is not acceptable anymore. So now engineers are debating that no, this should also be brought back. But the cost of bringing back is too high. So some owners can say that, okay, I will accept this cost, and you can bring back my criteria. So that is the fun part in performance-based design, that these limits can be moved back to this side, depending upon the client's interest, importance of the structure, or the money that they have. So performance criteria can be adjusted based on what is expected of that structure and what kind of money or resources can be spent. Another important thing that we always measure in a structure, and most of us are already familiar with that, is the DC ratio, demand over capacity ratio. What is expected, what is provided. That ratio is very critical. We expected this, we got this. That ratio tells us the efficiency of the system. So demand capacity ratio has been used as a measure traditionally to say this design is safe or unsafe. In a traditional code, if your DC ratio is more than 1, we say, oh, this design is failed, and we mark it cross. Actually, it means nothing. That DC ratio in the code more than 1 means nothing in reality. It just means DC ratio more than 1. That's it. We should not read any more meaning into that. Except for certain types of members, we will talk brittle members, we will talk about that. But that is why we have now 2 types of DC ratios. Members with brittle behavior, DC ratio is checked by strength, in which case that number is okay. In certain members with ductile behavior, DC ratio is checked by deformation in elastic. So for shear of a beam, because it is brittle, If the shear demand is more than the shear capacity, we will not allow it, because that will lead to brittle behavior. So we will like our shear behavior to be elastic. So we will measure it by the force deformation, force DC ratio. For a beam in bending or a shear wall in bending, we will measure it by deformation ratio. What is the maximum deformation that it can carry, like the maximum drift ratio, and what is the current drift ratio? So we measure the DC ratio from that, and then we can combine them together. And later we will see more interesting things about this one when we go to other topics. But this combination of these DC ratio gives us now new ideas to design the structures, because some members we can design as force controlled or based on the brittle concept, and some members we can design based on the ductile concept. Up to us now, we can decide what we want to do, right? So gradually we will move from force conventional design to capacity-based design. How do we do the evaluation? How do we do that? And the answer will depend upon what is the objective. What are we expecting from this performance evaluation? What performance levels are to be achieved? If we are only expecting the elastic or the frequent performance level to be achieved, design is easy because it's elastic. We don't need to do much. But if we are expecting the MCE performance levels to be achieved and checked, it's complex, highly complex. Depends upon the importance of the structure, as I mentioned earlier. Hazard level, available tools, what software do you have, right? If you don't have a software that cannot do this, of course you cannot do this. What can you do? So availability of the tools will be now important. A wide range of choices, linear static analysis, linear dynamic analysis, nonlinear static analysis, and nonlinear dynamic analysis, they are all available for us to use for doing the performance-based design. So basically what we are saying is, if behavior will be essentially elastic, that means we are talking about a low level of hazard, then regular structure with short periods, for example, can be analyzed by using linear static procedures are fine. What we are doing for code-based design is fine. For regular structures with long periods and irregular structures, linear dynamic procedures are better. Response spectrum are accurate enough, right? So this gives you an idea that if you have a certain, so now we're talking about both hazard level, type of structure. So the method to do the analysis will depend upon how high is the hazard level and what type of structure are we dealing with. If the structure is symmetrical, nicely done, simpler analysis can be used. If the structure is not nicely done, more advanced analysis is required. Similarly, if the risk is low, hazard is low, you can use simple analysis. If hazard is high, we require other tools. However, if we are talking about collapse prevention and MCE, we have no choice. We have to use nonlinear static analysis, pushover, and most likely nonlinear dynamic time history analysis if necessary, right? That means nonlinearity is essential if we want to do performance-based design for anything more than frequent earthquakes or anything more than simple structures. So that means we need to be familiar with these tools and the techniques behind them. So what is needed? Typical review objectives is to enhance the structural performance, obviously, improve serviceability, safety, and reliability, explicit check on various performance indicators, exactly check this, check, like that, to improve cost effectiveness. This is normally people think that if you do performance-based design, the structure will be more expensive. No, doesn't have to be, because we will know where to take out and where to add the reinforcement of materials and so on, because we will know which elements are critical, which are not. So non-critical, reduce the reinforcement. Critical, increase the reinforcement.